Hi, everyone. Today I will present our paper, An Extreme Multi-Label Text Classification XMTC Library Dataset. I am Jennifer D'Souza, and I work as an NLP researcher at TIB based in Hanover, Germany. This work is a collaborative effort with researchers from 3 other institutes, the Deutsche Nationalbibliothek, the University of Udine in Italy, and the National Library in Finland. Now, at the outset, I would like to define the task that we have addressed in this work, which is essentially subject indexing. So here is a simple definition of the task. Given a record's title and abstract, classify a top K rank list of relevant GND subjects. So the record's title and abstract is the input. The GND subjects is the subject taxonomy that is used for classification. More about the GND itself later. And the classification task is the machine learning objective. This can alternatively also be seen as a ranking task of relevant subjects to a given input record. Now, to be more precise, the specific machine learning variant of the task addressed in this work is what is called as Extreme Multi-Label Text Classification, or XMTC for short. It is typically the size of the taxonomy that is used for subject indexing or for classification that determines this task variant. So it's a very important factor. For instance, the TIB uses the full GND subjects taxonomy for indexing its library records. And the GND subjects taxonomy includes over 200,000 candidate subjects. This results in an XMTC benchmark, which involves assigning items to very large label spaces with the consequence of highly skewed long-tail distributions. Now, I would like to motivate the reason we performed this work. Libraries have long relied on expert subject indexing to make collections findable, interoperable, and durable. However, the growing volume and multilingual nature of library records has created a strain on these manual human expert workflows. At the same time, large language models and emerging agentic pipelines promise support. However, these systems also must be grounded in authoritative vocabularies, auditable, and evaluated in library terms rather than general classification scores. So a review of the field showed us that there were no existing XMTC subject indexing dataset to facilitate AI development. And this led us to introduce the dataset TIB-SID, which also stands for TIB subject indexing. So how did we prepare this dataset? Now, there are 2 parts to the dataset. The first is the subject indexing taxonomy, which is the GND subjects taxonomy, which is a standardized authoritative subject vocabulary used for indexing across German-speaking libraries. The second part to the dataset is the dataset of records itself. Now, these are the library records which have been annotated with subject terms. So our preparation of the GND was as follows. First of all, we obtained the GND subjects taxonomy from the source, that is at the DNB. Here we downloaded the complete sets. Now this page basically shows you the various GND taxonomies that are available. So the SAC-Begriff is not the only one. There are also GND vocabularies, for example, for person, places, location, etc. However, the focus of this work is just on the subject's taxonomy. Hence, our focus was relegated to these files. Now, this slide shows you a partial snippet of a GND subject term in Mark 21 XML format in the raw GND SAC-Begriff file. Note that this is a very heavily coded format, which almost makes this file unusable for AI and NLP researchers. Hence, what we did in this work was define a human-readable schema and convert this SAC-Begriff file or the subject's taxonomy file to the human-readable form. So this slide shows you 2 subject terms which are now released as human-readable data. So the first term corresponds to total organic carbon, and this subject term has, several other metadata items associated with it, like related subjects, the alternate names, and so on. And another subject term here, which pertains to holistic treatment. So within the GND taxonomy that we provided with TIB-SID has 207,000 unique subjects, which indeed makes this dataset an XMTC dataset. Now, how did we prepare the dataset of records, which is the second part of the data? Here we relied on the TIB-CAT open data. TIB-CAT stands for the TIB catalog. Now, a bit of context. TIB maintains a bibliographic collection of approximately 5.7 million records. And this collection is continuously growing, so the number 5.7 million will not remain a constant. Okay, so a part of the TIB's bibliographic holdings are publicly released to the community under the CC0 license, which is accessible through the library website. So it is this part of the data that we have released within the TIB-SID dataset. At the time of creating TIB-SID, there were approximately 200,000 records in the open data raw dump. And we downloaded the dump offered in the JSON linked data format. Now that we have this data set, for machine learning purposes, we want to create train, dev, and test splits. But we had a step before, which was data cleaning. Now, the data cleaning focused specifically on removing records with sparse languages. The raw data of the TIB is highly multilingual, records with no abstracts, sparse record types, and records that did not have any GND subject term annotations. Thus, the total resulting records that we released is 136, approximately 136,000. Now that we have this dump, we split the data into the train, dev, and test splits. So this table shows you an overview of the proportions of the records present across, the record types and also across the languages. Now, this table is discussed more in detail in the full paper. The TIB-SID dataset of library records is highly multidisciplinary. In total, it has 29 research fields. Note that these are research fields that are internal to the TIB. Some of the top domains are as follows. So there is a strong STEM presence. However, records are also present from specialized areas which form a long tail, example, mining. There are 166 records. Now, this slide shows you an example record of type thesis in the German language. So the title translated to English reads as follows: Experimental and Numerical Investigation of the Flow in Pumps with Low Specific Speed Considering the Influence of Roughness. So that is basically what the record is about. And this record has been annotated with 5 GND subjects, translated to English, some of which are pump, shear stress, flow, roughness, and so on. Here is another example record of type book in the English language. So here, the subject specialist deemed it sufficient to annotate this record with just one subject, that is financial mathematics. We've also released the data on Hugging Face to make it more accessible to the machine learning community. So this, in a nutshell, is what TIB-SID is about, or what TIB-SID contains. Now for some dataset overview insights. Note that this dataset is sourced from the real world. It is actually sourced from an operational public library. Therefore, the annotations contained in the dataset reflect a long-term annotation process, which includes staff turnover and workflow evolution and other kinds of peculiarities. This might present a challenge for robust AI solutions because they need to capture corpus-level regularities rather than idiosyncratic cases, and they need to support principal reasoning for library AI systems. We've also characterized certain features of the dataset itself. They are discussed in detail in the full paper. For the sake of this presentation, I will discuss only 2. The first feature being the long tail phenomenon. Now, from the approximately 200,000 GND subjects packaged within TIB-SID, 41,218 actually appear in the dataset. So there is a part of the GND that is not covered in the data. And these subjects include a mix of traditional and contemporary subjects. So we have observed a long tail structure indeed in the subject annotations, and frequent subject labels tend to coexist with many specialized ones. And only 6,164 subjects appear in all 3 splits. The implication of this is that AI models must support few-shot and zero-shot generalization, so not just focus on the head classes. Another feature is polysemy. So here we study how confusing the GND might be for machine learning, like how cleanly defined are the semantic spaces of the subject terms themselves. So we basically use the technical mechanism of embeddings, where all the subjects are projected into embedding spaces. And we look at how many nearest neighbors does a subject term have. And here we relied on cosine similarity with a threshold of 0.9. So we looked at how many subjects have any similar neighbors, how many subjects have multiple similar neighbors, and how large do these neighborhoods get. And indeed, we are studying this phenomenon for the G&D subjects taxonomy. So interesting enough, we saw that most subjects show no sign of polysemy. So this is reflected by the low mean neighborhood scores from the GEMMA and GINA models. And even for the E5, which showed a very high mean neighborhood score, on manual eyeballing, we saw that this didn't equal polysemy because the embedding model itself, that is E5, tended to form very large neighborhoods by grouping topically or morphologically related terms. So this basically reflected relatedness, not multiple meanings of the same concept. Okay, finally, to offer the community ideas of approaches that could be developed on our benchmark dataset, we have benchmarked 3 select systems. And I will go through the 3 systems one by one next. So the first system was created by Andrea Salfinger and her team from the University of Udine in Italy, and it works as follows. A new test query arrives. Their system finds 2 ways to match the new test record to subjects. So the first one is G&D concept match. So it tries to match the record against G&D concepts, and they call this the ontological reasoning branch. The second way is train example match. So they look at similar past training records and reuses their subjects. So they call this the analogical reasoning branch. Then results from both branches are merged and the closest matches are ranked highest. And finally, the top subjects are returned. The next is System 2, which was developed by Maximilian Kahler from the German National Library, and it works as follows. So a new test record comes in. The first step is retrieving similar train records. Note that this is something in common with System 1, this analogical reasoning component. Okay, after this, there is the completion step where an LLM is prompted to generate free-form subject ideas. And here they use the retrieved examples to suggest likely keywords via the few-shot prompting mechanism. Then they map the LLM keywords to official subjects using hybrid search algorithms. And finally, there is a ranking step where another LLM ranks the subjects to form the final list order, and the top subjects are returned. Systems 1 and 2 needed no training at all. Next is System 3, which was developed by the ANF team led by Osma Suominen from the National Library of Finland. Now, this system was trained, but before training, they invested some careful effort in preparing a strategic training dataset that would be effective in realizing a strong trained model for subject indexing. So here's how their approach was. First, they created 2 equally sized monolingual collections of the records. So they translated the 55,000 German records to English and the 44,000 English records to German. So they had these equal monolingual collections. Next, they generated synthetic training examples focusing on the G&D subject terms that were not covered in the training dataset. And here they created 4 variants of the synthetic training dataset records. And the selection of these 4, which basically leveraged 4 different language models or large language models. And this decision was made via a test of multiple different candidate LLMs. Finally, given this much larger training data set now, they trained 2 monolingual models, machine learning models, using some of the stable backends in the ANF toolkit. And then they combined these into monolingual ensembles. So that's kind of what the training process looks like. They have the regular ANF, stable ANF backends, the Bonsai, the MLLM, and the X transformer, which were trained, and then they combine them. So the combination of them to make predictions is what comprises the ensemble model. Now, unlike systems 1 and 2, system 3 is heavily engineered and is trained. So this is basically a brief look at the results. We provide more detailed discussions of the results of the systems and their performances, as well as short error analysis in the full paper. System 3 outperforms systems 1 and 2. We also did a study based on the performance of the systems on record types, on languages. We also conducted a qualitative study where we discussed with subject librarians in 5 different fields the predictions made by the 3 systems for 10 select records, and then they ranked which ones they liked, which ones they didn't like. So we had like a fresh view on the annotations, and these results are also present in the full paper. So now to conclude, some of the takeaways of this work, we provide insights for approaches. We've shown how LLMs can play different roles, so not just end-to-end prediction. For example, it can perform reasoning in embedding systems, in embedding spaces as shown by System 1. It can perform candidate generation or judging, data enrichment, and re-ranking. We've also seen that classical methods still matter. For example, tree-based classifiers or lexical matching and so on, which was used in System 3. And hybrid systems tend to outperform out-of-the-box LLM-only approaches. So the best results would essentially come from combining structure, retrieval, and LLM reasoning. Our implications of this work for library and practical AI can be seen as follows. The first one being that real-world data does not always include clean benchmark data. There are long-tail labels, as we've seen, there's distribution shift, and sparsity must be handled explicitly. Furthermore, LLMs can be leveraged in various ways given these limitations for translation, for data augmentation, for reasoning, and quality control. So finally, practical AI is certainly about trust and sustainability. So TIB-SID can be leveraged to develop transparent pipelines, to develop reusable models, and for cost-aware inference and human-in-the-loop readiness. So this QR code basically is the link to our paper, and we encourage you to read our full paper for more details on this work, as well as the link to the benchmark dataset. And we encourage the community to explore TIB-SID for your own XMTC and subject indexing research.